Let's talk about change of basis. Suppose we want to change the coordinates from one basis to another. Suppose b equals b1, b2. The font for this b is what we call Fraktur. This is the kind of calligraphy that was used in Germany in previous decades. Very cool. And c equals c1, c2 are two bases for a vector space V. Let's say x equals 5b1 plus 7b2. So the coordinates of x relative to the basis b are 5, 7. This is x in terms of the basis b. If b1 equals 3c1 plus c2 and b2 equals 4c1 minus c2, find the coordinates of x relative to the basis c. In other words, we know the coordinates of x relative to the basis b, and we want to use that to find the coordinates of x relative to the basis c. What is x in terms of c1 and c2? Here's how we'd solve that. If we want to switch from b coordinates to c coordinates, we multiply the b coordinate of x by this matrix. Okay, b1 sub c, b2 sub c, blah, 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 b sub n sub c. These columns are the c coordinates of the vectors in the basis b. Now, since we saw b1 equals 3c1 plus c2, that's b1 in terms of c, that's going to be our first column. Okay, these are the c coordinates of b1. And since b2 is 4c1 minus c2, our second column of this matrix is going to be 4, negative 1. Those are the c coordinates of b2. Thus, the c coordinates for x are going to be, okay, so we have this matrix. These are the coordinates of x relative to b. Multiply those together, and we get the coordinates of x relative to c. In other words, x equals 43c1 minus 2c2. We can check our answer. X equals 5b1 plus 7b2. We saw that earlier. But since b1 is 3c1 plus c2, and b2 is 4c1 minus c2, multiply all this out, and we end up with 43c1 minus 2c2, which we saw a moment ago was what the formula gave us. So it works. The matrix 3, 4, 1, negative 1 is the change of coordinates matrix from b equals b1, b2 to c, and we represent it with this symbol. For some reason, some authors write it like this, but I think it's kind of awkward. I would just write it like this, p sub b to c. So in other words, the coordinates of x relative to c is going to be this matrix, the change of coordinates matrix, times the coordinates of x relative to b. Suppose we don't know the conversion from b to c. In other words, suppose we don't have this information, so we don't know this kind of stuff. Suppose we simply know b and c in terms of the standard basis. So b equals b1, b2, and c equals c1, c2. And that's all we know. We just know the vectors in the basis b and the vectors in the basis c. Here's how we'd find the change of coordinates matrix, p sub b to c, from b to c. Put these matrices side by side. So again, c1, first column, c2, second column, b1, third column, b2, fourth column. And then use Gauss-Jordan elimination to get c1, c2 in reduced row echelon form. Everything you do to c1, c2 also do to b1, b2. When your left side, c1, c2, is reduced to I, the right side, b1, b2, will become the matrix we want, the change of coordinates matrix, p sub b to c. We've seen something like this before. This is what we did. It's something very similar to what we did when we wanted to find the inverse of a matrix. We applied row operations to get the left side to be the identity matrix, and then the matrix on the right side was what we wanted. Okay, here's why this works. This is a parenthetical comment. That's why I'm put in parentheses. You don't have to be able to follow this, but I just thought I'd tell you anyway. When you're converting the matrix C, C1, C2, into I, then you're converting the matrix B on the right side into C inverse B. Because basically, when you convert C into I, it's like multiplying it by elementary matrices. And the product of all those elementary matrices turns out to be C inverse. Okay, B and C do not convert X from the standard basis E1 to E2 to B and C. Actually, they do the opposite. So B converts from this basis to the standard basis, 1, 0, 0, 1. And this matrix C, okay, that converts our basis C to the standard basis. Thus, C1, well, C inverse B, converts a vector from B to the standard basis and then from the standard basis to C. In other words, this converts it from B to the standard basis, and then this converts it from the standard basis to C. So that's why it converts it from B to C. If you understood that, great. If not, that's okay. Life goes on. So suppose B equals 1, 2, 3, 4, and C equals 1, 5, 2, 12. Suppose these are two bases for R2. Find the change of coordinates matrix from B to C. Again, we're going to use elementary row operations to transform this matrix. So here's C, and here's B. We're going to use elementary row operations to convert this into the identity matrix, the 2 by 2 identity matrix, I sub 2. And then on the right side, we'll have P sub B to C. So this is our matrix, okay? 1, 2, 1, 3, 5, 12, 2, 4. Elementary row operations, first we're going to use this 1 to kill off this 5. So negative 5 times row 1 added to row 2. Here's negative 5 times row 1, add that to row 2, and here's what we end up with. So first row is still the same. That's still 1, 2, 1, 3. The second row, after you add negative 5, negative 10, negative 5, negative 15 to it, becomes 0, 2, negative 3, negative 11. Looks good, except I don't like this 2 here. We want that to be a 1, so we multiply row 2 by a half. First row stays the same. Second row is 0, 1, negative 3 halves, negative 11 halves. Okay, yeah, that's okay. That's all right. Okay, and now let's multiply row 2 by negative 2 and add it to row 1. We're going to use this 1 to kill off this 2. So here's what negative 2, row 2 looks like. 0, negative 2, 3, 11. Let's add that to row 1. And the bottom row is still going to be the same. The top row then becomes 1, 0, 4, 14. And we're done. On the left side, this is our identity matrix. So this matrix on the right side must be our change of coordinates matrix. 4, 14, negative 3 halves, negative 11 halves. To be honest, we could have used a graphing calculator to find the reduced row echelon form of this matrix. Because if you use reduced row echelon form of this, you'll end up with this. Again, you'll end up with that. So for example, if B equals 1, 2, 3, 4, and C equals 1, 5, 2, 12, and we saw those a moment ago, same bases. If these are two bases for R2, then the change of coordinates matrix from B to C is 4, 14, negative 3 halves, negative 11 halves. Suppose x sub B is 6, 10. Find x sub C. Oh, we can do that. We know how to do that. So you just multiply 6, 10 by the change of coordinates matrix. Multiply that together. Here's what you end up with. Simplify, and you end up with this nasty one, 164, negative 64. So that's x relative to the basis C. Okay, confirm that x sub C and x sub B represent the same vector. I don't want you to take my word for it. I want you to show you that this really works out. So again, we've seen that the coordinates of x relative to B are 6, 10. That means x is going to be 6 times 1, 2, plus 10 times 3, 4. Those are the vectors in the basis B. That works out to be 36, 52. And from C, okay, these are the coordinates we saw a moment ago what the coordinates of x are relative to C. So x should be 164 times 15 minus 64 times 212. Those are the vectors in the basis C. And you know what? It also works out to be 36, 52. It's great.